In this video, we're going to learn an additional method for solving quadratic equations. In particular, it's called completing the square. But before we get into learning this completing the square method, let's review the two methods we have already learned for solving quadratic equations. The first one we learned is called solving by the square root property. We use this on equations that were set up like the quantity of x plus 3 squared equal to 12. In other words, the square root property is really good for when we have these squared pieces like this. And then they can equal out to a number. Sometimes the squared piece is just an x squared and sometimes it's a quantity like this, but the square root property is good for solving these types of equations. So then the way we went about solving them was we would square root both sides, but on the right side we would insert a plus or minus with the square root. And that's essentially what the square root property tells us we have to do. Then the motivation for square rooting both sides is on the left. When we square root a square, the square root and the square operation cancel out. That leaves us with just the x plus 3. And then on the right, we just simplify the radical. And that would leave plus or minus 2 square roots of 3. And then with that, we're not done solving for x. To get x by itself, we would need to subtract off the 3. But what we do on one side, we have to do to the other. And then that leaves us with negative 3 plus or minus 2 square roots of 3. And that's our solution. It's actually two values in that. One of them is negative 3 plus 2 square roots of 3. And the other one is negative 3 minus 2 square roots of 3. So that gives you the two values that are solutions to the original equation. So that's the idea of the square root property. Now let's look at the other method we've covered for solving quadratic equations. And that's solving by factoring. Now solving by factoring we used on equations such as 2x squared minus 5x minus 3. The reason why we needed another method for solving quadratics is because if we have both an x squared term and an x term, then we can't use the square root property because I cannot get the squared piece equal to just a number, no matter how I manipulate this equation by adding or subtracting terms from both sides. So we resorted to our factoring techniques and using the zero factor property. Since this equation equals 0, then I can factor what's on the left side there and then set each of those factors equal to 0 and solve the resulting equation. In particular, this equation factors as the quantity of 2x plus 1 times the quantity x minus 3. And that's still equal to 0. And the equal to 0 part is key because that allows me to take each one of these factors and set them equal to 0, essentially breaking this one equation into two equations that we have techniques for solving. So that gives us the equation 2x plus 1 equal to 0 and the equation x minus 3 equal to 0. So solving the first equation there, I need to subtract 1 from both sides, and that's going to give me 2x equal to a negative 1. And then to finish solving, I'll have to divide by the 2 on both sides. And that means that x equals negative 1/2. So our solution, one of our solutions for this equation is negative 1/2. Solving the other equation is a little simpler because all we have to do is add the 3 to both sides. And that gives us that x equal to 3. So our solution for solution set or solutions for this equation is both of the values we were able to come up with. So our solutions are negative 1/2 and 3. So that's solving by factoring. And that gives us the two methods, solving by completing the solving by the square root property and solving by factoring. Now what we're going to do is turn to learning a third method called completing the square. Before we get into that specifically, I want to kind of motivate why this method is necessary. Consider the equation x squared plus 6x minus 4 equal to 0. Now, I cannot use the square root property to solve this equation because I have this x term. So if I were to get the x squared by itself, then it wouldn't equal a number. There would be an x on the other side, and therefore I wouldn't be able to get x by itself because there's multiple x terms. So solving by the square root property is not an option for this equation. This looks more like the type of equation that we would use factoring on. Now, in order to factor this trinomial that we have on the left, it's already equal to 0, so we don't need to worry about that. In order to factor that, we'll usually look at the number in front of x squared, which is a 1 in this case, and we can multiply that by a negative 4. That equals negative 4. Now, in order to factor this, I need to find factors of positive 6 that add to negative 4. Well, negative 4, we can make that by a negative 1 times a 4, or a negative 2 times a 2. I can make the 1 positive and the 4 negative. Switching the sign on the 2 is not going to change anything. These add to 3, 0, negative 3. None of those will add to 6. In other words, this trinomial on the left side of our equation does not factor. And we've seen trinomials that don't factor before. We called them prime. In this case, we're not going to say the answer is prime because this isn't a trinomial. We're trying to solve an equation. We just can't use factoring to do it because the part of the equation we need to factor doesn't factor or is prime. But that doesn't mean the equation is prime. It just means we need to find a different method for finding the value for x that will make that equation true. In general, all quadratic equations can be solved. So there is a solution here. We just need a different technique to come up with it. And the technique that will do that for us is this completing the square technique. And completing the square will actually solve any quadratic equation. Regardless of how it's set up or presented to us, it might take a little bit of work, but completing the square will work to find the solutions to any quadratic equation. So we're going to work on developing that method so that we can then solve these equations. What is meant by completing the square is basically we're going to be given an equation that's some sort, it can be in any configuration, but it'll be a quadratic equation. I'll just be boring here and give us that quadratic equation. So, but this one does not solve by the square root property. So the idea of completing the square is to go through some math aerobics to reconfigure the equation so that it is set up with a perfect square equal to some number. Okay? So in other words, we're going to take something that won't solve by the square root property and transform it into something that will solve by the square root property. In this process of taking a quadratic equation that won't square by the square root property and transforming it into something that will solve by the square root property is the process that we call completing the square. In other words, we're going to complete the square so that we have this perfect square binomial. We're going to complete the situation so that it has a perfect square binomial. I kind of think of it more like we're creating the square, but the traditional name for it is completing the square, so we'll stick with that. So that's the idea. In order to see how to work with this process, I want to go back to kind of the anatomy of a perfect squared binomial, because we need to understand that anatomy pretty well in order to work through this process of transforming an equation into having that shape. So I want to look at the quantity of x plus 3 squared. Now what I'm about to do is not the process we're learning, it's helping us to see how and why the process works. So when we have something like x plus 3 squared, in order to multiply that out, first of all, we cannot just distribute the exponent. That's the temptation, but that does not work. What we need to do is actually multiply the base, which is x plus 3, times itself. And then what we get is two binomials being multiplied. So we have to take every term of the first guy times every term of the second guy. So that's going to give us x squared for multiplying the first terms, and then plus a 3x, plus another 3x, and then plus 9. Now because these two binomials match, it'll always be the case that the middle two terms match, because we took the x times the 3 over here and the 3 times the x over here. So those will always end up matching. And then it's also the case that this guy will always be the last two guys multiplied, and since everything's twins, then this last term will be a perfect square. It's also the case that this first term will always be the first guy times the first guy, so since those match, the first term will also be a perfect square. In this case, it'll just be x squared. And then once we get that multiplied out, we can combine our like terms in the middle, giving us x squared plus 6x plus 9. Now these two guys that we combine to make like terms will always be twins, as we saw. So when they combine, they essentially double themselves. So instead of having 3x, now we have 6x. So what that means is that if we zoom in on our last number here, which we then doubled up here, okay? So this middle term is twice that number. It's 2 times 3 with the x, okay? Because there's two of them being multiplied. And then the last number is that number times itself. Now this isn't true with every trinomial when we multiply it from two binomials, but if the binomials are the same, the middle number will always be twice this last number in the original binomial. And the last number will always be that number squared. And so if we're going to create a binomial squared, we can use this pattern to elicit getting back to a binomial squared. Let's see how this works with a problem where we're going to start with something that's not a binomial squared and work backwards into having something like this. So this example one is kind of training wheels for our actual solving by completing the square. But here we just have a trinomial. It's not an equation, so we're not going to be solving. And we're asked to find the value that makes the following a perfect square. In other words, what number would need to go into the blank to make this fit the pattern we just saw? Well, what we just saw is if it is a perfect square trinomial, then the 12 came from adding twins. If we're going to add twins, those would have to be a 6x plus a 6x. Those would have been the two middle terms that this trinomial would have come from. And then the other thing we saw is that what goes in the blank here are those twins squared. So it would be a 6 squared, or 36. For those of you that prefer a formula approach, what you do is take this number that's in front of the x, and we usually call that b. So if you think of the equation you're aiming for, ax squared plus bx plus c, then the number in front of x is the b. So for our formula, we would take b and we divide it by 2, and then we square that quantity. And then that gives us the c that we're looking for. You can do it by just thinking about breaking twins apart and squaring it, or you can divide by 2 and square. It's the same math either way. So that's the idea. Now what we have here, x squared plus 12x plus 36, this problem doesn't ask us to do the factoring, but if we did factor this, it would factor as x plus 6 quantity squared, or one of those squared monsters. So we're going to use this technique of manipulating the equation to get what we want with this. But this wasn't an equation. This was just to show you this idea of coming up with the number necessary to get the problem to behave the way we want it to. Now we're going to move to an example where we're actually going to solve an equation by completing the square. So what we saw in the previous example was kind of this fill in the blank activity. And what we want to do here is set our equation up to do that fill in the blank activity. In other words, this one right now is kind of in the place where we filled in the blank, and we need to get it out of the way. Luckily with equations we can do whatever we want as long as we do it to both sides. So what I'm going to do is add the 1 to both sides of the equation in order to clear it out of this slot. So when I add the 1 to both sides of the equation, what I end up with is x squared minus 10x equal to 1. And I left a little space there because, like I said, we're doing this like we're going to figure out what goes in that blank like we did in the previous example when we were figuring out what number it'd take to make it a perfect square trinomial. So basically the idea here is we are assuming that our first two terms make up a perfect square trinomial, and we just need to figure out what the third term would be for that to be a perfect square trinomial. And any numbers that aren't behaving, that constants that aren't behaving, we kind of just get them out of the way so that we can reconfigure the left side to be a perfect square trinomial. So what we did previously is we thought, okay, if this negative 10x is a perfect square trinomial, is a part of a perfect square trinomial, that means that it would have come from adding a negative 5x and a negative 5x. That's the twins that would have added together to make it. And then if we take that coefficient, the negative 5, and we square it, that's what goes in our blank, the negative 5 squared. Now here I got to do a little bit more than I did in my previous example, because that previous example was just training wheels on coming up with this number. But now we're dealing with an equation. And so the whole thing that allows us to get away with just inserting some number that we came up with is that whatever we do to one side, we have to do to the other side. So I'm going to add this negative 5 squared to the other side as well. I usually don't write this as the quantity squared. I'm just writing it as negative 5 squared right now so you can see where it came from. Usually what I would do is just add a 25 in there because that's what negative 5 squared is. And we'll get to where that step and where we just leave out this intermediate step. So the formula approach on that would be to take the negative 10, divide it by 2, and square it. And of course that equals a 25. Okay? So, like I said, I usually don't write it as 5 squared. What this would usually look like is the same thing, except writing it as a 25 instead of a negative 5 squared. So, that's the idea of completing the square. So when we talk about completing the square, that's what we've just done. But the reason why we did it was to transform our equation into something that could be solved by the square root property. We've not solved yet, so we need to keep going. Now on the right here, I can just do the math, and that's 26. On the left here, what I want to do is go ahead and factor this trinomial. And if you want to go through your factoring trinomial method, you're welcome to, but I already know because I constructed this trinomial to behave in a certain way that it's going to be a binomial squared. My first term's an x squared, so that'll factor down to an x. And then the constant on that's going to be a minus 5. And where I'm getting that from is it's half of the coefficient of my middle term. Or you can think of it as what you had before you squared. And so that's going to be what the constant is in the binomial squared every time. And the reason why I know that is because I created the trinomial to behave that way. That's the idea of completing the square. So once we have it in factored form, what we now have is something that we can solve using the square root property. So we're going to take and square root both sides. When I do that, on the left here, the square root and the square cancel each other out, leaving me with an x minus 5. On the right, the square root of 26 doesn't simplify, so that'll just stay plus or minus the square root of 26. If it did simplify, I would simplify it. Okay? And then we're not solved for x yet. To finish it out, we need to add 5 to both sides. And so our final result is that x equals 5 plus or minus the square root of 26. And that's the idea of solving a quadratic equation by completing the square. Again, I want to emphasize that the completing the square process is what we did here to turn our equation into something that had a perfect square trinomial on the left. And then the constants on the right are just the consequence of our manipulation. Okay, the rest of it is applying the square root property that we already knew how to do. Alright, so that's kind of a straightforward example. We'll do another example that has a little bit of a curveball in it. Alright, so example 3, solve by completing the square. 2x squared plus 12x equal to 4. Now if you compare this back to the previous example, there's two things that are structurally different about this equation. The first thing is actually kind of helpful, and that's that the constant is already on the right. Whenever we complete the square, and as we did in the previous example, we want to get the constants so that they're on the right. You could think of it like we're storing them over there. That's not mathematically what's happening, but you can think of it that way. The other significant thing that's happening differently with this trinomial is that we have in front of the x squared a number, and when we complete the square, you don't want your coefficient of your x squared to be anything but 1. So we're going to have to deal with that, and that's really the big difference between this example and the previous example, because in the previous example it was already a 1. So basically we want to be able to get down to x something quantity squared, and for that first slot to be an x, then the number in front of x squared in the beginning needs to be a 1. So we've got to deal with that. The way I usually say that is that our general setup when we're completing the square is x squared plus bx, where b is some number, we leave a little space there, equal to a number over here on the side, and then we figure out what goes in the blanks from there. Okay, but we're not ready to figure out what goes in the blank until those numbers in front of x squared is a 1. So over here in our actual problem, what we need to do, remember we can do whatever we want as long as we do it to both sides of the equation. Well, I can get rid of that 2 if I divide by 2. So I need to divide the left side by 2. And whatever I do on the left, I have to do on the right. And it's important to remember here, I'm dividing the entire left side by 2. So I'm going to distribute that division to both of my terms when I do the division. So what that ends up looking like is x squared plus 6x equal to 2. And then I like to just put the little blanks in there that we're going to be filling in. They're kind of cute. Kind of cute. Alright, so now we're to the point where we want to try to complete the square. Or, you know, think about, okay, what goes in our blank? When I talk about now we're ready to complete the square, I'm saying, okay, now we're ready to figure out what goes in the blank. And we cannot do that. You cannot figure out what goes in the blank until your number in front of x squared is a 1. It'll throw everything off if you do it before then. So what we did to figure out what went in the blank was we thought about our twins that our middle term would have come from. In this case, it would have had to have been a 3x plus a 3x. Okay, and then what goes in the blank would be that number squared, so it's going to be a 3 squared, which is a 9. So we're going to add 9 into the blank. What we do on the left, we have to do on the right. For those of you that are preferring the formula approach, we're basically taking the 6, dividing them by 2, and squaring, and that equals 9. And once we have that sorted out, then I know that this trinomial on the left is going to factor as a binomial squared. I know the first slot's going to be x. That was why I did this whole part where I had to divide off the leading coefficient if it was anything but 1. So because the only way to factor an x squared is into x and x. So that's how I'm getting that guaranteed first term to be an x. Okay, and then after that we got the second term by half of the linear term's coefficient. So in this case it's half of 6. And that's going to be a plus 3. So that's what we have on the left side. On the right side we just do the math, and that would give us an 11, I think. So that's completing the square. We've done it. We've completed it. Yay. We've not solved the equation. Completing the square turns the equation into one that can be solved by the square root property, so now we're ready to square root both sides. And when we do that, the square and the square root on the left side will cancel each other out. And then on the right side, that doesn't simplify, so we'll just be left with plus or minus the square root of 11. And then to finish it out real quick, we subtract off a 3 from both sides, and that leaves us with x equal to negative 3 plus or minus the square root of 11. So, and again, just as a reminder, I always like to throw out there that this is two values. So our solution is negative 3 plus the square root of 11, or negative 3 minus the square root of 11. Two separate values. We're just using shorthand to put them together. Alrighty, so that's the idea of completing the square. Go ahead and give some of these a try and see how you fare.